Well, controllable factors where the word controllable itself says which is under your control on a ship, which you can control. What can you control on a ship? Well, what you can control on a ship is, tell me. Speed. So how do you control the ship speed?
Propulsion system.
Very good. Propulsion system. What else can you control?
Direction.
Very good. Direction. Propulsion system will gives you a control over speed and your steering system.
Direction.
It gives you your
Direction.
direction.
Ship stability.
Ship stability. Basically, you can say your ship stability, or you can say draft. Yeah, that plays your underwater ship's volume will indirectly affect both steering and propulsion. Yes. So these are the factors which we will then intricately look into. I have this website. You can note this website. This is a very good LNG company, and they have their own very good website. AnthonyVader.com. You can visit their website. You can find volumes and volumes of information there. They keep doing innovations, they keep researching into things. So where will you find the non-controllable factors in the industry, which are propulsion, steering, your ship stability? All these factors, they continue changing as per the needs. Needs of what? Needs of operation, design of the ship, yeah, design of the industry, needs of the market, how fast you want the ship to go, how maneuverable you should want to go, where your area of operation, where your ship is going to operate. Then who would be going about doing research based on this? Would be these operators. Yeah. So this is one of the very good operators. Now what you see in front of you, if you can see here, is it's an LNG feeder vessel. Yeah. This is an LNG feeder vessel. Is there on your website. Now you can see that you are seeing this vessel in a. This is the solid mode and this is the X-ray mode. You can. It's a 3D model of a ship, which you can then turn about, and then we can. It's a very good way to demonstrate things here. Yeah. So what I want to. Where is the propulsion system? Well, that's your propulsion system here. Can you see it? Yeah, something driving it, and this is your propeller here. Your steering system is somewhere over here again. Yeah, and it has additional systems to maneuver it as well. You can see a bow thruster here. Yes, and there is a stern thruster. You can see somewhere here. Can you see all of that? Yes. Now, based on ship stability and whether the vessel is loaded, whether the vessel is in ballast, will decide the underwater volume of this vessel. Yes. Now, what consideration for the persons who are operating on these vessels would be that this propeller always remains immersed, come what may. One of the operational limitations that you might say, or you can say one of the controllable factors that is there in your hand, that you can decide upon, that you make sure that this propeller is immersed underwater. If this propeller is not immersed underwater, then some of the controllable factors like propulsion and steering will then start slipping away from your control. Agree? Okay. So, basic stuff. We are starting off with basic stuff. We'll look into more detailed things. What else is also a controllable factor is, but that is right from the initial stage. Yeah, is the design of the vessel. Yeah, design. Yes, different kind designs of the vessel. Yeah, So what will then play into the maneuverability, which will then lead on to decide whether how maneuverable a vessel is. Then trick design will then lead to this conclusion that how a maneuverability of a vessel is going to be affected. A basic principle is this is the length of the vessel and this is the breadth of the vessel. Basic stuff. What affects maneuverability is the length by breadth ratio. When we are talking about maneuverability, what are we talking about maneuverability? We are talking about how fast can a ship go, how straight can it go, and how directionally stable a vessel is, and how good is the vessel in turning. That is what a ship does. That is what you need. Yeah. Even for your cars, you have a turning circle. Yeah. So this plays a very major role at the design stage, at the initial stage itself, into these components. How good a ship is. A directionally stable vessel means if this is a directionally stable vessel, for example, this is just a mere example of ship, a model here. If a ship is directionally stable and its propulsion system is on, it is making way through water, yeah, and you leave the rudder, steering, the directional controlling device right in the center. You're not giving it. We will look into the propulsion system and the rudder, how it works, how it affects, what is the flows around the rudder, and all the other details as well. Let's say, for example, layman's term, the ship is moving, and if you leave the rudder to midship, a directionally stable vessel will hold its direction for a very good duration of time. Yeah. For a directionally stable vessel, generally the profile or the underwater volume or the design of the ship will be the length will be way more. Yeah, the length to breadth ratio is going to be higher. For example, container vessels. Yes, container vessels, they are way longer than they are fatter. Yeah, they have a very less beam as compared. So length over breadth. Generally, a vessel of, let's say, a 300 meters long container versus let's say a beam of say about 40 meters. Can you do the math here? What would be the ratio here? Very quickly. 7.5, yeah? Pretty high ratio. Let's compare it to a fat vessel. A length of, let's say, VLCC. Yeah? Some of you have been on VLCC. General length of about 330 meters and a beam of about 62 meters. Can you just calculate this?
So 5.3.
5.3. Yeah, you're saying?
And also for maneuvering, it's the other important thing is the V shape or U shape.
Yeah, we will look into that. Yeah. Now this is a length versus breadth ratio here, and this is the length versus breadth ratio of a container. We are looking at two extremities first. It is always easier to look things from the point of view of extremities. These are two extremes. Ship which is block shaped, yeah, moving bulk as well. That ship is not block shaped, more streamlined. Yeah. And then of course there will always be ships somewhere in the middle range. Well, you can't talk much about ships that will lie somewhere in the middle, can you? You can always good to draw conclusions from extremities, and then you can apply it to other kind of ships. What is this going to affect into the maneuverability of this ship? Well, let's look into it. Fat ship. Just giving example, a VLCC. Yeah, length 330 meters, beam 62, and you said it is what, 5.3?
Yeah, 5.3.
The ratio is 5.3. This ship, do you think this ship is going to be directionally stable? Something like this, for example, it is not going to be directionally stable, it's very fat. But when a ship is not directionally stable, it will be very good. Turning, the turning circles will be somewhere around, you can say 2.8 times the ship's length. It will turn. It will have a sharper tighter turn. It will turn well because of this thing, length to breadth ratio. It will not be directionally stable. It will need controllable factors like you have the steering will continuously need to be applied on this ship to keep it directionally stable, keep it going. But if you needed to turn it, well then it will turn quicker. Tighter turn.
Quicker?
Quicker, of course it will be quicker because it is shorter turn and it will be tighter. For a vessel which is on the other hand, I told you a container vessel, 340 container vessel. Well, this container vessel is going to have a bigger turn. What did we say? This was 7.1. But this vessel is going to be very directionally stable. You will not need to apply continuous and regular steering application, the rudder again and again to control this vessel. It will steer very well. Speed will be higher. Okay? It can achieve higher speeds. The profile is designed in that way. Go quicker. Again, meet the needs. So that will be the result of this two extremities of your. Well, on an LNG ship, you can yourself decide what kind of a ship that would be, length to breadth ratio. Now you know how to play with it. Where does it fall? Is the length to breadth ratio very high? Well, if the length and the ratio of the vessel that you will be on is very high, well, you will yourself know that it is going to be the turning of this vessel is going to be difficult, but steering of this vessel in one direction will be easier. But if the length to breadth ratio is very low, steering will be difficult to maintain its heading, but it will turn really well.
What is the normal length of the LNG or LPG that we use?
Depends. See, again, depends on the amount of volume that it carries. 200,000 CBM LNG vessel would be somewhere around 350 meters long. 150,000 CBM would be about 270 meters long. Depends on how much are you planning to carry. More you want to carry, bigger the ship. Less you want to carry, smaller the ship. The one that I just showed you was the feeder vessel. Quite small, about 150 long. Small ship. Feeder, the word feeder. Yeah? But built for purpose to move things about here. Happy? Now I will look into some of the slides based on these two factors that we just discussed. This is what we were discussing. Yes, hull form that will initially decide upon some of the factors that you can control this factor right from design stage. But this factor will then be based on the needs of where the vessel is going to operate, area of operation, volume that you want to carry. Yeah, variable factor. Every ship cannot be designed in the same way. Well, there is something called coefficient of finesse. Yeah, what is coefficient of finesse? It is basically the underwater volume of a ship. how it will decide how a vessel will travel in a straight line without deviation, that we were talking the same thing about. This will again be addressed when you are going to do stability. So you can make this point. So vessels with larger block coefficient. Well, what is block coefficient? Block coefficient is how closer a vessel's underwater profile is to a rectangular box. See this ship? It's going to have very high block coefficient based on this, how it looks. Almost like box shape. Yeah? But if I make it more streamlined over here, shave these sharp edges here, shave these sharp edges here, make it more streamlined here. Well, then what will happen? The block coefficient will decrease, coefficient of finesse will increase, and this vessel will then suddenly become more directional. Why is a ship built like this? So that it can carry more, you can carry more in a box, square box. But if you just exactly make it like a box, what will happen? It will become very difficult to move it in water. So, reasonable compromise, that's what you can say, based on the needs. Now we were talking about one of the controllable factors to control the vessel speed is propulsion system. Okay. Now we will not look too much into details because 90% of the marine vessels out there are being driven by fuel oils, heavy oil, diesel oil. Yeah. Some of it now LNG is taking over during this course. Again tomorrow after lunch, one of my colleagues, he will look into the LNG propulsion systems. We'll give you the more detail of the LNG propulsion systems. Well, based on the vessel's propulsion needs, you will be putting in the engine on the ship. Some would be a slow speed engine, yeah, which are going to be a deep sea vessel, which is going to run for a longer duration of time. Yeah, where you need we do not need very high maneuverability, but you need very high efficiency. It's a give or take between maneuverability and efficiency. And your need to use the engines, need to use the control. How often do you need to control it? How often do you need to control it? Well, a ship, if it is designed to move from one part of the continent to other part of the continent, are you going to keep on moving it again and again? No, you will achieve one speed, steady speed, and you want that ship to continue on that steady speed for the better part of its voyage. Yes? Yes. So for that kind of a ship, a bigger engine, a slow speed engine with lesser RPM, yes, with higher efficiency is required. You are not going to gain any higher efficiency by increasing the RPMs, pumping in more fuel and increasing the revs, are you? No. So you would want something big, slow and steady that can keep on running at the same pace slowly forever and ever, don't you? So that would be then that kind of a ship. A bigger LNG ship which is moving 200,000 CBM of LNG in a bulk from one continent to the other continent would have a slow speed engine. Maybe RPM of 80, 90 or 100. One big, very big propeller. It will then slowly keep on turning and keep on turning. But then it will have limited maneuverability, because to create maneuverability you need smaller propulsion systems specifically placed, running at higher RPM so that they can move about more and then achieve what is required, higher maneuverability. Yes? Makes sense to you? Yes. That's what will be the design consideration: medium speed, high speed marine diesel engine. Smaller ships, like the smaller feeder vessels that I showed to you, is it going to have a slow speed diesel engine? No. Unlikely. Yeah? It might have a steam turbine, LNG carrier, and it will be running on higher RPMs. Okay? Moving on from here, what then comes? What finally moves the ship forward? A propeller. Yeah, propulsion system we have talked about, the need for the propulsion system, the requirement for the propulsion system, the guiding principles behind putting a propulsion system on a ship. Then comes the propeller, which finally delivers the push that the vessel needs. Well, there are different designs, again, based on different, needs, maneuvering needs. Something that is going to be very big is not going to give you a very high maneuverability. necessarily. Yeah, something that is small and maneuverable, which can move about and which can go up and down on its RPMs, and which has got more streamlined flows. Those will be more used on smaller ships. Yeah. The basic design, like you can see, is a fixed pitch propeller. You will come across this design while we going into the bridge. Before that, we will discuss you and I will show you what kind of a ship you have. What is the propulsion system propelling your ship? So you must have already come across these terms, two basic terms: a fixed pitch propeller and a movable pitch propeller. You can say controllable pitch propeller. Yeah. What is pitch basically? Well, pitch is basically when is the distance that the propeller from its, let's say, this center point, it will travel when it completes one full revolution. When a propeller completes one circular revolution in water, we are going to measure the distance that it is going to cover. That would be the pitch of this propeller. Will then again be, if it is related to the angle at which the blades are designed. Yeah. That is what a fixed pitch propeller is. Its pitch is going to remain fixed. So to control your vessel speed, what you are going to do is you are going to increase the RPM or decrease the RPM, the number of turns. You can't do much. One factor is stationary, or you can say it's fixed. Another factor, you are having two factors. You can change the pitch, or you can change the revolutions, which will then directly relate to your vessel's linear speed, or the propulsion that you are generating. So in this case, propeller, the pitch is fixed. So what are you left with? RPM. So if you're going to change the RPM up and down, what is going to happen? That would then decide how fast or slow this ship is going to be propelled. In another kind of design, like what kind of ships will be will have a fixed pitch propeller? Well, again, suitable for ships that do not require a high degree of maneuverability, like I talked about. Something we are fixing it. We are trying to minimize cost. We are trying to minimize efforts. We are trying to minimize things here. So that will bring up automatically cost. Something that is big, low installation cost and maintenance. Of course, there is less maintenance is required over here. Well, you see this small thing over here as well. Well, this is called a MoS cap fin. This is the better part, or in the beginning of this century, this is an invention that has come about not more than 1 decade or 1.5 decades ago. What it does is it increases the efficiency of the ship. We will look into it later on. We will show it to a video as well. How it makes the flow more linear. Yeah. This increases the efficiency of the ship. This you might find in more newer designs and ships. The increasing the efficiency of the propeller will directly reflect on the fuel consumption and minimizing the cost. Yeah. Controllable pitch propellers. Controllable pitch propeller, what is happening? The angle of this blade is going to change. So you have both the factors are variable here, which are in your control. One, RPM. You can play with the RPM. Two, you can play with the pitch. But generally, these are smaller ships. They are put on smaller ships. The smaller vessel which require high maneuverability. To change the RPM of the ship again and again and over is not very efficient. Quite inefficient to do that. You also know it. Yeah. If you run your car in first gear and you keep changing gears again and again, is it going to be more efficient? No. So you run it in one efficient mode. So what is going to happen here? The RPM is going to be steady in this case. Generally, you can change it if you want, but generally the RPM will be made steady, and what they will play with is the pitch of the propeller. They will change the angle of the blade. If you change the angle of the blade, the pitch will increase and decrease, which can then relate into speed. So you don't have to go again and again go and change the RPMs, leading to different fuel consumptions, spike in fuel levels, engine stress levels, yeah, constant need of one person manning the engine room. Yes?
What is the maximum angle for the blade?
Technically speaking, I will not be able to comment on what is going to be the maximum angle of the blade. Yeah?
To reach the maximum speed,
This is far too. I have not looked into it, but I will definitely try to answer it. I will note one of these points and I will get back to you on this one. Well, if you have a zero pitch, how is the blade going to be? Just flat.
Yeah. No angle.
No angle. Yes? And if you change the angle, what will happen? It will start.
Yeah, that's moving.
Yeah, it will start moving, throwing water back, and it starts moving. Yes? Now, what is another considerations is, you can see up to 3 times expensive than a fixed pitch propeller. Maintenance is going to be high, more movable parts. Yes? It is vulnerable compared to fixed pitch propeller due to moving parts, additional seals. Propeller efficiency is slightly lower due to large hub. Hub is the part that is behind a propeller. You see this extending part? That is called the hub. So you need more devices in the hub to control this. You need more parts to control the angle pitch of the blade. So hence you will end up having a bigger hub. Well, this bigger hub will cause poor flow. Yes, and that will reduce the efficiency. Well, do not consider this officer the watch. Well, this has to do with your collision avoidance and all the other factors. Another problem is zero pitch that a lot of people don't know if they are not aware of it, or not sailed on these kind of ships. Let's say your ship was moving. Yes, with a good linear velocity, for steering, and suddenly you make your pitch zero. What will that do? It will not cause any propulsion, but that leads to another problem, because your ship is continuously turning at an RPM. It will make your propulsion, the steering system that you have. You have a steering system. That steering system, we will look into it later on, is indirectly responsible. Yeah, it is only effective, not responsible. It is only effective because of the amount of flow of water passing through it. This is one of the design limitations. What you're going to do is, if you make the pitch zero, you're just creating a wall behind the one of the controllable factors, your rudder, the steering system. You're making it uncontrollable again. This is one of the design considerations that you have to. So if you're making your pitch zero, then you have to be aware of this fact. We will end up not steering the vessel. The vessel might just go wherever it feels like. You are losing the directional stability of the vessel. Get this point?
Yes.
This is one point that you have to bear in mind. Well, another kind of propulsion system, duct propulsion system. This is your propeller itself. This duct can change the direction of the flow of the water, which then itself can act like a steering system in itself.
It's also movable.
Yeah, you can change the duct. It is just like, if propeller wash is coming, it is creating water flow behind the ship. If you charge changing the direction of this water flow, what will start happening? The vessel will start turning. It is one of your controllable factors. You can then steer the vessel.
On this consideration, we don't use the rudder.
When will you use the rudder? You can use the rudder, then will maximize your efficiency. When will you change the flow of direction? Out there at open sea? No. Out there in open sea, you will keep this steady and you will play with this to control your vessel steady. But when you are at slower speed, you can use this to achieve what you might not need a tug or any other external propulsion system, or you can say a outsource propulsion system. Increase your maneuverability. Well, what is it? You can say it is going to, first of all, increase your efficiency of the propeller. Yeah, you're going to make the flow more linear. Yeah, more. You're going to duct it rather than losing it. So produces greater thrust at lower speeds, particularly useful on vessels with high propeller load such as tugs and trawlers. Again, it's going to be on smaller ships where you need higher maneuverability. It's going to have lesser efficiency than unshrouded propellers at increased speed of 10 knots due to drag onto the duct. This additional thing at higher speed, it's going to be counterproductive because it is going to start creating drag, friction. Yes, this device, when a flow is coming around from the ship's side towards this propeller, what is this duct going to cause? Friction, drag. It itself starts converting into drag. Does that make sense? Then at higher speeds, it will start affecting the efficiency. Another kind of propulsion system, azipod. Well, it is electrically driven propulsion system. Yes, it is going to be hanging outside your ship. Very high maneuverability might be expected out of these ships. As you can see, propeller which is fixed. If we have the ships, if you have these, you can see there is no rudder around it. There is no need of any steering system. This itself is more in its own a steering system, steering capability. It can give you a vessel direction as well as speed all by itself. Can you see it? It does not require rudder. So it is in one way minimizing cost as well. It improves fuel consumption due to decrease in hull resistance because there is no shaft, there is no propeller, there is less things that is going to create drag at the faster speeds. Decrease noise and vibration. Slight reduction in course keeping ability due to flat stern design. Yeah, you are not streamlining the flow. So slight reduction, what the rudder blade does is it streamlines the flow and it allows your vessel to become more directionally stable as well. But this one, with so many of them going in one direction, the flow from one might go and hit the other one, and it might cause different pressure fields. We will look into a pressure field around the rudder or behind the propeller, what happens. That might cause the ship to become slightly directionally unstable. Make sense?
Is it recommended to use it in larger vessels?
It is generally, you will find it in vessels which are passenger ships, cruise ships. Yeah, you might offshore supply vessels. Yeah, which needs to do very peculiar maneuvers all by themselves. Very, very high maneuverability. Now we are talking about the steering system. So basic conventional rudder. This is a basic conventional rudder. Now what this rudder does is it when you move a rudder about in this kind of a situation, it is going to cause two things. One is it is going to cause drag, and one it is going to cause lift. Yes? When you move this from this main normal streamline, what is it going to create? It is going to create one lift. Lift is what? Direction that it is going to try to push the vessel, and drag is because the resistance to flow that it is causing. Okay? What do we want out of a rudder is maximum lift. We try to maximize the lift out of a rudder. That is what we want. Because we are interested, we use this device to do what? Control the direction of the vessel. We do not want unnecessarily drag here. That is minimizing the efficiency. But that is, you can't help it. It comes with it. Yes? So if this would be a ship, here, and if this was the rudder, well then you have given this is a starboard rudder, starboard helm. What does this cost? A high pressure system around here and a low pressure system around here. So what will the ship try to do then? It will try to shift towards it will try to turn the stern of the ship towards the low pressure system, and it will eventually start turning your ship in the starboard direction. That is how it works. Make sense? This rudder is only effective if there is flow of water passing through, flow of water around it.
No flow.
No flow, no lift. Yeah, no flow, no lift, no drag either. Higher flow, higher lift. So when the velocity of water passing through it is higher, then even at small angle you can create high lift. Well, the velocity of water, flow of water around it is less, the velocity of water passing through this rudder is less. Well, then you will, to create that same lift, you will need to give larger deflections. Make sense? So it's a give and take. You will have to decide what you want to do based on your needs. So common sense, if you are propelling out there at sea, in open sea, yeah, at higher maximum RPMs or your maximum higher engine efficiency at maximum vessel design speed, well then you are not going to be moving about a lot. You don't need to actually move about a lot to get the direction. Why? Because high velocity of water is passing through it, even slightest of deflection will create the required lift that you need. But at slower speeds, somewhere in harbors and ports, when you cannot, for the purpose of safety and for the purpose of approaching, for the purpose of controlling, you will yourself realize in some of the exercises in future that when you are limited with the speed of approaches, because you cannot go at very high speeds. Speed is going to be controlled. Well then, for the same lift that you need, to give it a direction, you will need to create a larger deflection. That you have to again bear in mind. Different kinds of rudders, balance, semi-balance, yes, we will look into it. Most vessels are fitted with a semi-balanced rudder. What a semi-balanced rudder is going to be is, it is going to be fixed down, yes, and it can then move out from there. Again, that was the basic design of a rudder. This is a Becker rudder. It is like a fin of, yeah? It's like a tail of a fish. Can you see this? Another bit here. Yeah. What is this going to do? Create higher lifts, increase the lift of the ship. Because this bigger portion of this rudder can only go to a certain, the area of operation of conventional rudder is about 30 to 40 degrees on either side. What this does is, adds another tail to it, and then it can increase the lift. That is one of the designs. To achieve lateral thrust, some headway is required. Maximum rudder angle should be limited when on sea passage. Yes? Because what will this cause? It will cause, if you are at very higher speed, then you start doing this, what will this result into? A great amount of strain and stress and drag on the rudder. Yes, vibration, stress. But this is designed for vessels, again, which we need higher maneuverable needs. Chilling rudder. What is a chilling rudder? Well, it is again not looking like a normal conventional vessel, conventional rudder, but this can turn all the way almost to 70 degrees. And can you see the design of this rudder here? Fishtail design. So what it does is water flows through it and it picks up speed. At slower speed, if you see, it can be turned up to a 70 degrees with this design. Can you see the design? You can turn it at really, really large angles. What that allows is, especially this curve here, can you see this curve here? Mm-hmm. When you turn it at higher degrees and the propeller wash is coming, it can throw this and it can then laterally move the ship. Yeah? higher motion can be achieved at almost stopped conditions. You can control your vessel's turn to a very greater degree, as you would be able to control it later on with just, you can say, with a conventional rudder, you will not be able to do so much. But with this, with higher degree, you can turn it. You can create very high lift, all the propeller, and it will guide the flow of water in that direction, and it will create that lift that you need, and you can actually do these kind of movements. Again, operational needs of a vessel, maneuvering needs of this vessel. Another controllable factor, thrusters. Simple propulsion systems, based, they're based along the forward and aft center line of the ship, to move the ship bodily. Fixed pitch, you can see it, and you will see it on your bridge as well. Basically, they are basically fixed pitch propellers. Yes, but what is the design consideration? The flow of water around it, the linear speed of the vessel, the forward and aft speed. If your vessel is operating at a very high speed, this is going to be ineffective. There is not going to be enough flow around it. So their design consideration is the consideration that you will have to play into, or you will have to bear in mind before you start operating this is, what is the linear speed of the vessel? Only below a linear speed they would be effective. But then they can guide the flow of water in either direction that you want. Well, if you have this, your vessel, these would be only there required on vessels which actually then do not depend on external or outsourcing needs for the factors of maneuvering a vessel. This kind of a ship does not need any other ship to assist it in maneuvering. Complete solution in itself to maneuver. Come alongside a berth, get away from a berth, go into any restricted port, a dock, without any external assistance. Yes? Yeah?
What about that part?
Which part? This one?
Yes.
Well, this is a duct propeller there. Movable duct propeller for the forward.
No propeller on the
This side?
yeah.
There might be one there as well. But this is just an example that we are showing. There might be one aft as well. Well, thrust is going to be created perpendicular to the ship. But if your ship is moving and you create a thrust, well then it is not going to be perpendicular. Okay, put it.
Yes.
Now I'm going to give you this. I'm going to give you a printout after lunch, the kind of ship that you will be on, which then you will have to read yourself, and I will also explain it to you, which will give you all of these design characteristics of a ship, including the propulsion system, all the factors that are controllable, that can be found in your vessel's pilot card. One piece of data that can be presented to anybody, or even you can glance through, and you can, in one very quick view, can find out the design characteristics and the limitations or the design of the controllable factors that are present on the ship to control the direction and speed of the vessel. So we're going to watch a video now. Yes. Make notes during the video. Yeah. Why is it not? Oh no.
A ship slowing down and stopping at the end of her voyage. A situation encountered by all ships. A ship slowing down and stopping at the end of her voyage.
Did you just see this? This is this vessel's telegraph. Yes. In our simulator, it is not going to be like this. So I'm highlighting it to you. Vessel is one of the controllable factors that we were talking about. Propulsion. So you cannot increase your vessel's RPM by 1 RPM, 2 RPM, 3 RPM. Vessel engine is designed. Generally, this is a slow speed diesel engine. Yeah. So it is designed to work at certain levels or RPM. And for the general conventional method of communication as well, you are not going to, the person that how we have trained people as well at sea, is not going to say make RPM 10, make RPM 20 or make RPM 30. Yeah, there are a set way of saying things. So you can see, as you can see, it is mentioned here, one is stop. Well, stop is 0. Yeah. Even if in the stop position, if it is a CPP ship, stop means the pitch is going to be 0. Then it is, you can see, it will start with okay. So it will start with, I'll write this down. It will start with, you can say, dead slow head. You can see dead slow, a slow, half, full, and then your vessel's maximum 100% setting of the engine. So in our, if you want to write this down, in our bridges here, you will not going to see this in the telegraph, slow, dead slow. What you are going to see is 2, 4, 6, 8, and 10. 2 means 20% of your engine's maximum performance output. 4 means 40%, that is your dead slow head. 6 means 60%. 8 means full head, 80%. And 10 means 100% of your engine's RPM or performance. Yeah, output.
So it equals 20, right?
Roughly. It is not 100%, but the roundabout. What you need to know is maximum of the vessel's maneuvering happens between half to stop. Between your vessel's 50% to 0% of your vessel's engine's performance. If you are going anything beyond that, well, that is either for your longer deep sea passages for a steady direction maintenance, or for otherwise you are just going to be operating for your vessel. When your vessel is operating in and around a port, it will be in this range, maneuvering. Always another handy tip to bear in mind is keep the 50% always for emergency use. Do not always use all full 100% of your vessel's maneuvering capability when you are maneuvering in close quarters. Keep always 50% if you need it to go the other way. Control, slow and steady. Okay?
A ship slowing down and stopping at the end of her voyage. A situation encountered by all ships during their normal operation. Stopping and low-speed maneuvering are part of the beginning and end of every ship's voyage, and the forces involved in these maneuvers are important to all who handle ships. As the ship slows down, the rudder forces reduce, and other transverse forces can dominate the handling characteristics of the ship. This film will investigate the interactions between the ship's propeller, hull, and rudder. Their effects when stopping or maneuvering at low speed.
Now it talked about transverse forces as well. What is your vessel's propulsion system doing? Passing because of the longitudinal forces that are applying in the forward and aft direction, your vessel is either moving forward or vessel is either moving aft. Also because of the inherent design of the hull form and the type of propeller and the rudder and the stern hull form, there are going to be some transverse forces working athwartship to the ship. Yeah, which are also important for ship maneuvering. You will look into this, so I'm just highlighting it. It just mentioned two things, transverse forces, so you must be wondering because we did not cover that in slide. So your vessel is designed to go like this, generally 90% of the time, but when your vessel is actually maneuvering, coming alongside to another vessel, your vessel needs to do this as well. Yeah, move athwartship. Well, these transverse forces then you need to be bearing in your mind and be then deciding onto what you need to do to use these transverse forces to your advantage when you are doing this close quarter maneuvering, when you're going alongside, going off, bearing that in mind. So because of the hull form and the type of the propeller that you have, every ship has an inherent design of the transverse forces that come into play, which will then decide where the vessel is going to go. You will look into this. I will also explain this at the end of this video, give you some rules to play with.
Will be demonstrated. The tanks and models of the National Maritime Institute of Felton are used to show effects that are difficult to see in the ship. For this film, a right-handed propeller is used throughout. Most ships are fitted with a right-handed propeller, one which, when running ahead, turns clockwise as viewed from the stern.
So just now it highlighted one type of propeller, that is your, I will keep writing this down on the board, is your right-handed propeller, which when you view from stern is going to turn clockwise. Yeah, I already explained to you what is fixed pitch propeller, what is controllable pitch propeller. Well, each can then either be right-handed or there is another type of propeller is left-handed propeller, which is going to be turning in the opposite direction and viewed from the stern. Okay.
A common situation. A ship steaming ahead under still wind and water conditions with helm amidships, slowly swinging to port. In the tank, we find the same situation. Here the effect is more pronounced as the ship and model are directionally unstable. Tufts being fitted to the stern and rudder of this model to show the water flow and how this flow causes the propeller, hull and rudder to interact. What is the effect of interaction between propeller and rudder? When running ahead, the propeller accelerates a body of water astern, shown by the ship's wake. In addition, it gives the water a helical motion, seen when the propeller is close to the surface. This helical flow alone will not give rise to a transverse force. But what effect does the flow have on the rudder? In most cases, the helical flow from the propeller does not strike the rudder uniformly. Here on the starboard side of the rudder, the flow is straight and fast at the bottom, but slow and unsteady at the top, thus reducing the pressure on the rudder in this area. Using a mirror placed on the far side of the model, the port side shows no unsteady flow, and therefore no reduction in pressure. The pressure on the rudder shown by the blue arrows is higher on the port side. This will tend to cause a gentle turn to port. What is the effect of interaction between propeller and hull? First, the basic hydrodynamics of the propeller blade moving through the water are explained. A cross-section of the propeller blade is shown moving through the water at a small angle of incidence. The blade will produce a drag, the red arrow, and a lift, the yellow arrow. At a greater angle of incidence, the lift and drag increase. The drag forces act in the plane of the propeller's rotation, and the lift acts parallel to the propeller shaft. As long as the water entering the propeller disc has the same velocity over the whole area, and its path is parallel to the propeller shaft, the lift and drag generated by each blade are equal. Under these conditions, there will be no net transverse force caused by a deeply immersed propeller. Unfortunately, when a ship is running ahead, this is not the case. Over the hull of this model, whose propeller has been frozen photographically, the water flow entering the propeller disc has an upward motion, shown by the tights. The propeller's rotation causes the relative angle of incidence of the downgoing blade on the starboard side to be greater than that of the upgoing blade on the port side. The yellow arrows show the resulting imbalance of lift forces when the blades are near to horizontal, caused by the upward motion of the water. This will tend to turn the ship to port. A ship moving through the water tends to drag some water along with it due to skin friction. This is known as the boundary layer and can be seen on the surface close to the ship's side. Below the surface, the boundary layer will affect a considerable portion of the propeller disc. At cross-section level with the propeller, the rate of flow is represented by a darker blue for a reduction in flow rate. This is known as a weight diagram. This example of a single screw ship shows how much of the propeller is affected. The darkest blue area represents a reduction in velocity of 80%. This variation of the velocity of water entering the propeller disc changes the relative angle of incidence to the rotating blade. The red arrows show the resulting imbalance of drag forces in the upper and lower sections of the propeller disc. This will tend to turn the ship to starboard. Three component forces have been shown to act at the stern. 1. The helical flow striking the rudder, tending to turn the ship to port. 2. The upward flow into the propeller disc, tending to turn the ship to port. And 3. The variation in flow velocity into the propeller disc, tending to turn the ship to starboard. The net resultant of these forces is commonly known as transverse thrust. For most single-screw ships, it causes a gentle turn to port. Now consider a different situation. When the propeller is turning astern, the water generally enters the propeller disc at a uniform velocity and direction, so there is no transverse force generated by the propeller alone. However, the propeller still produces a helical discharge, and when this strikes the after body of the hull, viewed here from below, it induces a down and inward component of flow on the port side, and an up and outward component on the starboard side. This causes a higher pressure on the starboard quarter than on the port quarter, which pushes the stern to port. The resulting turn to starboard is pronounced when carrying out a crash-stop maneuver in deep water. In shallow water, this effect is less, as the small underkeel clearance restricts the transverse component of the flow. A further effect when the propeller is turning astern is that reverse flow over the rudder can occur, even when the ship has considerable headway. In this case, the effect of the rudder will be reversed. As the propeller diameter reduces in proportion to the rudder depth, the effect is less pronounced, but still significant. When the propeller is stopped and the ship has headway, there is turbulence over the whole rudder and a consequent reduction in its effectiveness. This model is moving ahead with an equivalent ship speed of 7 knots. Rudder effectiveness is further reduced as the model is in shallow water. How do these interactions between propeller, hull and rudder influence a stopping maneuver? The There are several maneuvers which can be used to slow or stop a ship. Crash stop, when the propeller is put to full astern from full ahead, can be used. A considerable loss of rudder effectiveness and a large transverse thrust occur, resulting in a pronounced turn to starboard. This turn can result in a large change from initial heading and takes the ship well off the intended course. In deep water, the maneuver can be expected to bring a ship to rest in 7 to 10 ship's lengths. This large tanker model came to rest in an equivalent of 10 ship's lengths. If the engine is simply stopped, as in an inertia stop, there is little to retard the ship. The resistance of the hull to forward motion can be as small as 1/2000th of the ship's weight, even at full speed. Hence, this maneuver results in a greater stopping distance than the crash stop. In addition, there is a small lateral force due to the helical discharge from the stopped propeller impinging on the rudder, causing a slight turn to port. Forces other than a stern power can be used to retard the ship. The hydrodynamic drag, part of the resistance to forward motion, can be increased by moving through the water at a drift angle. A maneuver which benefits from this increased drag is called low-frequency rudder cycling. Here, in deep water, the rudder is initially put hard to port, and when the ship is about 40 degrees off course, the rudder is reversed. When crossing the initial heading, the rudder is returned to hard to port. Engine revolutions are reduced in stages. When crossing the initial heading again, the engine is put full astern, and the rudder hard to start. Depending on the turning characteristics of the ship, the stopping distance can be less than that for a crash stop. This ship model stopped in the equivalent of 6 ship's lengths, with a small deviation off course to port, and the final heading was close to the original. However, when the underkeel clearance is small, the ship turns with a negligible drift angle, so loss of speed due to the hydrodynamic drag is less than in deep water. Alternatively, given sufficient sea room, the benefit of increased drag due to the drift angle in deep water can be obtained by maintaining a turn to port or starboard with rudder hard over and reducing engine revolutions during the turn. Hydrodynamic drag can also be generated by the rudder and increases with rudder angle. The maneuver, called high-frequency rudder cycling, or fish-tailing, uses this increased drag. Here, the rudder is put hard over from side to side as quickly as possible, and the engine revolutions reduced in stages. The drag produced by the rudder increases significantly once stalled. This generally occurs at rudder angles between 35 and 40 degrees. When stalled, less lateral thrust will be generated by the rudder to turn the ship. This maneuver can be used to slow a ship with minimum deviation from the ship's intended course, and its effectiveness does not vary significantly with water depth. The stopping distance will be greater than for a crash stop, as it depends on rudder drag alone. When stopping, it should be remembered that the time required to reverse engines varies from ship to ship, and often steam turbine-propelled ships only develop about 40% of their ahead power when going astern. In shallow water, the handling characteristics of ships, particularly when using astern power, are variable, due in part to random shedding of vortices from the quarters. Here, during a crash stop in shallow water, the ship model has swung to port. The transverse forces that have been shown are only some of the forces influencing the ship when stopping or maneuvering at low speed. Others being wind, tide, and interaction effects. None of these have been covered in this film, but it is important that they are taken into account when handling a ship. To recap, some of the forces which influence the behavior of a ship.
Yes. Now we'll just recap this on the board, and I'll give you some rules, David, which you can note down as well. So, what to start with, there is going to be a fixed pitch propeller. Let's talk about fixed pitch first. So there are going to be 2 types. Let's say for fixed pitch, for every type there is one right-handed propeller, and there is a left-handed propeller. The right-handed is turning when you view from stern in a clockwise direction. and the left-handed is turning in a anti-clockwise direction. Yes. So the thumb rule is what you came to a conclusion. Let's talk about the fixed pitch propeller, right-handed propeller. When the vessel is going ahead, and we are talking about a single propeller at the moment, and the vessel is going to go ahead, it is going to turn to port. Yes. And when the vessel is going to come astern, the stern is going to come to port. Yeah. This will completely be opposite again on a fixed pitch left-handed propeller. When your vessel is going to go ahead, you're going to go to starboard, and your vessel is then going to come come astern. Well, then the stern is going to go to starboard. How can you remember this? Well, use your hands. This is your right hand. You use your right hand, and the way I remember it is, you see the curvature of your head. When you go ahead, your bow is going to port. When you come astern, your stern is going to come to port. When you do it with the left hand, you achieve the same thing as here. Make sense?
Yes.
What is going to happen when you have a controllable pitch propeller and a right-handed propeller? So when your vessel is going to go ahead, it is going to behave like this, just like a fixed pitch propeller going ahead, because the blade angle is always going to be the same as the angle of the blade here. Make sense? But when your vessel is going to go astern with a CPP and a right-handed propeller, what is going to happen is, it is going to behave like when it goes stern for a left-handed propeller. So it is going to go like this. Again, for a CPP, left-handed propeller, when you go ahead, there is not going to be any change. But when you go astern, it will start behaving like a right-handed propeller going astern, fixed pitch right-handed propeller going astern. So it is going to go in, stern is going to go to port. So again, remember CPP going like this. Sorry, fixed pitch propeller, right-handed propeller is going to do like this, but a CPP is going to go ahead and then come astern like this. Okay? Make sense?
Yeah.
Easy to remember? So before we can watch another small video.
DMT's ship handling series dealt with the ship's response to turning maneuvers, forces at work, and their effect upon the vessel's handling. The second film looked at slowing and stopping procedures and the special needs of very large vessels in shallow waters, or where sea room is restricted. This film expands the subject of ship handling further and investigates the situation where the unlikely has become a reality. The vessel is disabled and control is lost. Because of the potential for disaster, when a large vessel is drifting, perhaps on a lee shore or close to an oil rig, some basic questions need urgent answers. Firstly, if the failure is detected before becoming disabling, what can be done to ensure that the ship's head pays off in a preferred direction? Set the broad drift away from danger. Secondly, what is the direction and speed of drift? Thirdly, what can be done on board to influence these factors whilst repairs or a tow are being arranged?
For 20 years.
Fourthly, what are the priorities? These, then, are your priorities in the next vital hours. In classrooms ashore, the study is theoretical. Practicing with a real ship is better. But in any event, the primary forces and your ship's response to them must be fully understood.
Chosen here a VLCC with a rounded bow, in ballast, and a 50th by the stern, which is a fairly typical condition. The maths for this is very complicated. We wouldn't expect you to work it out on board, but we have worked it out here on the computer. The ship is heading east and the wind is from the south. And initially the ship is moving at 5 knots, but gradually the wind forces take over. And we can now see that it's drifting steadily in a north-northeasterly direction whilst heading roughly east.
Computer programs at Liverpool Polytechnic and model studies at BMT have given a better understanding of the behaviour of a drifting vessel. Though a VLCC model is used in these studies, the same principles apply to other ships and barges whose behaviour can be similar. If a stationary vessel in still water is subjected to a strong wind, the aerodynamic effect causes a lateral force, a longitudinal force, and a turning moment. Aerodynamic effects are shown in red. As the vessel starts to drift under the action of these forces, the hull's hydrodynamic effects come into play. These are shown in yellow. The steady drift of a vessel is determined by a balance of these forces. The blue arrow shows the vessel's track. The Earth's rotation generates the well-known Coriolis force, which in the northern hemisphere acts to the right. Coriolis always acts at 90 degrees to a vessel's track. Since track speed is low when drifting, the Coriolis effect can alter the track according to latitude. Subject to these forces, the vessel now turns to a new heading. This balanced steady state is represented by the equilibrium ship's heading, drift speed, and direction. And under these conditions, the vessel is sailing. At model scale, the action of the forces involved is studied in detail. The hydrodynamic effects are determined for a series of drift speeds and a variety of heading angles. The effects of trim and heel, although small, are also investigated. In the wind tunnel, aerodynamic forces on the exposed superstructures are established for a series of wind directions and for different conditions of heel, loaded and trim. The draft of the vessel has a substantial effect on its drift speed and direction. Analysis of experiments shows that for a large tanker in Beaufort 7 conditions, a change from light to low draft will slow down the freight by 1 knot, cause a 30 to 40 degree heading change. A change of draft will also cause the aerodynamic and hydrodynamic centers of pressure to change their positions. Change of aerodynamic center of pressure is particularly evident with all arc ships. The aerodynamic force will decrease as the hydrodynamic resistance increases. The couple resulting from these changes will produce a new equilibrium position and drift speed. Trimming a vessel will cause a similar but less marked effect. Heading and drift direction will change as the turning moments alter. This has little effect on the longitudinal and lateral forces and therefore does not significantly alter the drift speed. The same principle, trimming, is used by windsurfers to steer their boards. The movements fore and aft of the sail's center of pressure is used to alter the board's heading. This model represents a tanker of 300,000 tons in ballast draft, drifting in Beaufort 7 conditions, almost directly downwind. Notice that the drift speed is quite fast. With the wind still in the same direction from the top of the picture, but now in the loaded condition, drift speed is much slower, with some sternway. In model tests, space and time limits the full effects of response to wind, but useful indications of yaw and weathercocking due to high superstructure aft can be observed. In a container ship, where the effective superstructure is more evenly distributed, the drift tracks may be almost straight downwind.
We'll try to do the same today in the simulator. We'll try to blow the
In some ships, alterations to heel and trim can be used for fine-tuning of the drift track. Typical alterations for 7 conditions are a change of heading of 5 to 10 degrees, resulting from a change of heel angle of 6 to 10 degrees. In calm weather, the drift motion of a ship in deep open seas has the speed and direction of the current. But in rougher weather, waves also cause a ship to drift by momentum imparted from the waves as they are reflected off the vessel. Both the frequency of encounter and the roll period of the vessel can alter the effectiveness of this transfer of momentum. The freely drifting model in this wave tank clearly shows the effect of wave action isolated from wind effects. The film has been speeded up for convenience. In both loaded and ballast conditions, the model moves forward quite considerably, although drift speed is slower when loaded. As it would at sea, wave action also causes rolling. at the forces and moments due to aerodynamic loading, hydrodynamic resistance, and now wave loading will determine the resultant equilibrium heading. This in turn will give the drift direction. For some ships, there may be two headings which satisfy the equilibrium condition, giving 4 multiple drift directions with the prevailing wind on either bow. The equilibrium condition is not always stable, however, and a vessel's heading may suddenly change without obvious cause. And so, knowing whether your vessel drifts with headway or sternway is vital. For if engine failure, for example, occurred to windward of a headland, the head may be allowed to pay off, and the vessel sailed safely out of danger. The red area shows the possible drift sector of this headland. It is interesting to note that the ability of this vessel to sail is almost as good as the upwind performance of old-fashioned square riggers. This model bulbous bow tanker, ballast, is drifting in Beaufort 7 conditions. Whilst heading 93 degrees off the wind, the track made good was 150 degrees from the downwind at 3.5 knots. In the load condition, the track was quite different, 203 degrees against 150 degrees when in ballast. Relatively small alterations on otherwise similar hulls can cause quite major changes in the forces operating, and the resulting drift characteristics. For a round bow VLCC in Beaufort 7 sea state, this is a typical track when in ballast. This, when loaded. It is predicted that the vessel would make slight sternway, but in lower sea states, this could become headway. However, the bulbous bow VLCC usually shows headway in both ballast and load conditions in Beaufort 7 sea states. These results apply only to a particular vessel and its associated class in Beaufort 7 conditions. For example, evidence suggests that some coastal tankers would drift downweather, stern or bow into wind. In the case of a smaller tanker, we would expect the drift speed to be higher. Some gas carriers, a high drift speed and a positive headway. It is clearly important to know the characteristics and response of your vessel in advance, should a breakdown occur. During normal operations, it is not unusual to drift off ports where rapid shelving offers little anchorage. At such times, a valuable record of the ship's drift characteristics can be built up by accurately plotting your position and allowing for currents. Drift may be controlled in limited power.
Okay. If you see all of this, make do today wind, we will stop the ship. How it goes in the wind ship. What will depend is how deep is the ship water. We will do one with wind, one with differently with current. What you can see. Then one we will do with both wind and current, because then both wind, the ship's windage, the windage area will come into effect in underwater area, because it is a balance of the two. At sea there will never be one condition where there is no current, and we'll put ship without current, without wind in high waves, see how the vessel drifts away. Yeah. We don't need to go into the bridge. What I can do is I can load the ship over here, create the condition, show you the condition. You can increase it, make it into a time lapse. You can yourself see how it is behaving with the vessel track.
Okay, what? The vessel is gonna be loaded or unloaded?
We will do both the conditions. Okay. We will do loaded, unloaded, shallow water, deep water. Also, we will do rudder stack cycling. We saw the stopping maneuvers. How to stop a ship if the ship is going at sea with full speed. How much distance you are going to go? Keep going ahead if you go astern, or if you do turn in a shallow water, turn in a deep water. You will see all of this. We will do all of this today, quickly, one by one, so that you can yourself cement your knowledge or agree with what you have learned, that okay, this is what is going to happen. Okay? Okay. So we'll break for lunch. After lunch, you have a 2-hour session in meteorology, yeah, about wind, wave, weather patterns with my colleague Ian Brown. So be here at 1 o'clock, and then I will introduce you to the simulator at 3 o'clock, the meteorology session, and then we will do 1 hour of. Do you want this PPT for the